Today's video will deal with the last topic of nitrogenous compounds, which are the diazonium salts. We have mentioned before that nitrogenous compounds include the nitro compounds, whether aromatic or aliphatic, the amines, whether aliphatic or aromatic. We said that they include the nitriles, the cyano compounds, and the amides, but these were discussed in other classes. And finally, we have the diazonium salts. What are diazonium salts? They are compounds that have a nitrogen which is triply bonded to another nitrogen and attached to a benzene ring. As we mentioned before, diazonium salts have to be aromatic diazonium salts. Aliphatic diazonium salts are unstable compounds. They do not exist to a great extent. Very, very few examples are present of aliphatic diazonium salts. How do we prepare diazonium salts? As I've mentioned, in case of amines, you can refer to the class of amines, the video for the amines. Diazonium salts can be prepared from a primary aromatic amine. You have to start with a primary and aromatic. Primary aromatic amine. So you have a benzene ring and a nitrogen, which is a primary amine attached to it. You add, as we mentioned, nitrous acid at 0 to 5 degrees centigrade, and you end up with the diazonium salt. As I have mentioned before, there is nothing called nitrous acid. We do not have a reagent available in the lab called nitrous acid. Why is that? Because it gets easily oxidized, air oxidized, converting into nitric acid. So accordingly, what we actually start with is sodium nitrite in HCl. Or in any acid. It doesn't have to be HCl, hydrochloric acid. It can be any other acid. And the whole idea of this reagent is based on the fact that stronger acids replace weaker acids in their salts. What does that mean? This is the main idea that you have used when you were identifying the different salts in analytical or inorganic chemistry. When you actually had a salt, something like sodium nitrite, its actual acid is the nitrous acid, for example. So what do? You add a stronger acid. You had the sulfuric acid was the strongest, followed by the hydrochloric acid, followed by something like the nitrous acids and the other acids. So what you do is that you add a stronger acid, something like hydrochloric acid. What happens is that the hydrochloric acid is the one that should be the salt. It's the strongest acid, so it should replace the weaker one in its salt, which means that the chloro is the one that should be as the salt. So this gives the sodium chloride, releasing the other weaker acid. This is the whole idea of this method. You rely on the fact that stronger acids replace weaker acids in their salts. So you add an acid which is stronger than nitrous acid, and you add the nitrous acid as a salt. You add it as sodium nitrite. Accordingly, the stronger acid will be converted into the salt, and it will release the weaker acid as a free acid, which is the nitrous acid. And this is how you prepare this reagent. How did you do this in the lab? If you remember when you were preparing the azo dyes, what exactly did you do? You had 3 test tubes. The first tube, you added some sodium nitrite and you dissolved them in water. The second test tube, you had an amine and you added HCl, conc HCl to this amine. The last test tube, you had a phenol and you added some sodium hydroxide to this phenol. Let's see what were we doing in this test. What were we actually preparing? First test tube had some sodium nitrite. You started adding the first test tube to the second test tube. What was actually acting was the sodium nitrite. It was reacting with the HCl in the second test tube to give the nitrous acid. Once you prepare the nitrous acid, it reacted immediately with the amine present in the same test tube. It didn't not need any further additions. It immediately, as soon as it is released, it reacts with the amine. It reacts with the amine, the aromatic primary amine, to give you the diazonium salt. And then you added the product to the third test tube. What was in the third test tube? It had a phenol. This is the structure of a phenol. And you added some sodium hydroxide to this phenol. Why did you add sodium hydroxide? To abstract the proton, putting a negative charge on the oxygen of the phenol. Why is that? So that it would highly activate the ring, putting a negative charge on the ortho and para positions. This negative charge will attack the nitrogen of the diazonium salt, giving you what we call the azodie. This is the benzene ring of the diazonium, and then you have the two nitrogens now, and then the benzene ring of the phenol and the oxygen of the phenol. This is what we call azodies. What are these? These are dyes. These are dyes. They actually give color to whichever you put on them. You can use them to color leather, clothes, whichever. So whenever you prepared this azodie in the lab, if you remember, it used to color your hands, and the color used to stain your hands for a very long time, because these are dyes. These are dyes. These are coloring materials. They can color fabrics, and they can color leather. Okay, this was the reason, or this was the principle for the test of azodie. What is the mechanism for the preparation of the diazonium salt? The mechanism relies on, as we mentioned, you have nitrous acid in presence of something like HCl. You have a lone pair of electrons on the oxygen. It gets protonated, giving the nitrosonium ion. Now you have the aromatic, primary aromatic amine, and you have the nitrosonium. The nitrogen of the amine has a lone pair of electrons. It will attack the nitrosonium. You have the benzene ring and the nitrogen of the amine, and the nitrosonium is now attached to the nitrogen of the amine. If you look at this structure, it is very similar to this structure. What is the second structure? What is this? This is the keto form that you can actually perform tautomerism to give the enol form. If you remember, a hydrogen being transferred from atom number 1 to atom number 3. 1, 2, 3. And the double bond moves to the single bond. They are interconverted to each other. So this is exactly the same as the structure that you have now attached to the benzene ring. You have a double bond on atom number 3, and then you have, this is atom number 2, and this is atom number 1, and it's having a hydrogen. So you can actually run the same principle of tautomerism. And now you have a nitrogen, which is doubly bonded to a nitrogen, which is singly bonded to an OH. The hydrogen moved from atom number 1 to atom number 3. 1, 2, 3. And the single and double bonds were interchanged or interconverted to each other. You still have acid medium, and you have a lone pair of electrons on the oxygen, so you can protonate this oxygen, releasing water. You lose water, giving the form, one of the forms of the diazonium salt. This is one of the forms of the diazonium salts, and the other form is when this nitrogen resonates its electrons to the second nitrogen and carries the positive charge in its place. This one is the preferred structure of diazonium salt. Why is that? Here the nitrogen carrying the positive charge is alpha to the ring, so it is stabilized. The positive charge is stabilized by the ring. However, in this structure, the positive charge is on the terminal nitrogen, so it has no source of stabilization except this nitrogen. So this is how we draw diazonium salts. And the counter ion present in your acid, you had, for example, hydrochloric acid, so you will have chloride here. If you were using sulfuric acid, so you will have sulfate salt here. If you were using tetrafluoroboric acid, if you remember in the synthesis of aromatic nitro compounds, you use tetrafluoroboric acid, you will have tetrafluoroborate, and so on. Whichever acid you were using, use the acidic radical of this part, use the chloride, the sulfate, the whichever part you are using as a counter ion for your diazonium salt. This is how diazonium salts are prepared. Remember, we said that diazonium salts, in case of their preparation, you actually have to use a primary aromatic salt. Primary aromatic salt. We said that this is because if you use the aliphatic salts, aliphatic amines, if you use the aliphatic amines and you prepare the aliphatic diazonium salts, it is totally unstable. It loses a molecule of nitrogen, giving the alkyl group as a positively charged moiety. In presence of water, the oxygen will attack the alkyl group, giving the alcohol. So this is one problem, forcing us to only use the aromatic amines. Why do we use the why do we use the primary amines? Because if you're actually using a secondary amine and you react it with the nitrosonium, the first attack will take place. However, the tautomerism will not take place because now your nitrogen is not carrying a hydrogen, it's carrying an alkyl group. So you cannot perform the tautomerism that we did in case of primary amines. So in this case, you will end up with the N-nitroso compound. You will stop at the N-nitroso compound. How about tertiary amines? If you have a tertiary amine, you have no hydrogens, so if you reacted with the nitroso positively charged nitroso group, you have no hydrogen on this nitrogen to attack this nitroso group. What actually happens is that the ring is the one that will attack the nitroso. Now the nitroso is acting as an electrophile, and you have a benzene ring having electrons in it, so you end up with the C-nitroso. The nitroso group moves to the C position of the benzene ring. It moves to the para position of the benzene ring. Since you have an electron donating group substituent, your substituents will be directed, your other electrophile will be directed to the ortho or the para, and since there's huge static hindrance at the ortho position, then your nitroso group will go to the para position. I don't need you to know all these precautions. I just need you to know that you cannot use except primary aromatic amines, and that if you use aliphatic amines, you will end up with an alcohol. The precautions of the secondary and the tertiary amines, I'm just mentioning them for your knowledge. However, I will not examine you in them. So this is what we have just mentioned. We said that to prepare diazonium salts, you need a primary aromatic amine. You add sodium nitrite and HCl, so you're actually adding nitrous acid, but we do not have what is called nitrous acid, so we prepare it in situ during the reaction. As I have mentioned before, you have to perform this reaction at 0 to 5 degrees. And as you remember, you were doing this experiment in ice. You had the 3 test tubes in ice, and whenever you did an addition, you returned the test tube to ice immediately. Otherwise, the azodie will not be formed. You prepare the diazonium salts. This is its structure, and the mechanism is first the formation of the nitrosonium ion, followed by the attack of the amine on the nitrosonium, followed by your equilibrium. This is an equilibrium. It should be drawn like that. And then losing a molecule of water, giving the two forms of the diazonium salt. As I've mentioned, this is the stable form of the diazonium salt, and the aliphatic diazonium salts are unstable. They lose a molecule of nitrogen, giving. Now, if we discuss the reactions of diazonium salts, I have already discussed one of these reactions. We can first classify them into reactions where we retain the nitrogen, we keep the nitrogen, or we lose the nitrogen. So you can keep the nitrogen of the diazonium or you can lose it. I have already, in case of the retaining, discussed the formation of the azo dye, where you actually had the diazonium salt, the third test tube. Remember, adding the second test tube to the third test tube, and you added a phenol to this compound in presence of a base to give you the salt. As we said, the negative charge moves to the para position, attacking the diazonium salt, giving the azo dye. Why are these compounds highly colored? Let's look at their structure. Usually colored compounds are formed when you have a very long conjugated system. Color comes from conjugation. The longer the conjugated system, the more colorful your compound is. Let's look at this compound. You have here 3 double bonds that are in conjugation, in resonance with each other. They are conjugated double bonds, double, single, double, single, double, single, and then you have here the double, single, double, single, double. So they are conjugated through the diazonium part, the azo part, with the other ring, and again you have the oxygen with its negative charge or the lone pair of electrons as a part of this conjugation. You have a very long conjugated system. This same reaction can be performed by phenols or by amines, because again amines have lone pair of electrons, so they can donate them to the ring and put a negative charge on the para position, attacking the diazonium salt. And in this case, instead of drawing the diazonium with an O at the end, you're going to draw it with an amine at the end. Both of these are azo dyes. They are used to color leathers, fabrics, and so on. The other reaction in which you retain the nitrogen is the reduction reaction. You can reduce diazonium salts exactly like you reduced nitro compounds. You can, as you remember, use zinc in HCl, and usually zinc in HCl gives the amine. It doesn't give anything else, it gives the amine. So if you actually take a diazonium salt and you add zinc in acid medium to this diazonium salt, you will end up with the amine. However, if you use another reagent, which is the stannous chloride in HCl in sodium sulfite. This is another reducing agent that you can use. You will end up preparing the hydrazine, phenylhydrazine compounds. You retain both nitrogens. So in the first reaction, you actually retained one nitrogen. In the second reaction, you retained both nitrogens. Okay, remember, in order not to get confused which one produces which product, remember that zinc in acid medium always produces the amine, just an amine, not a hydrazine, not a hydroxylamine, not an azo compound. It produces the amine. So zinc in HCl will give you the free amine, while adding stannous chloride in HCl and adding a reducing agent like sodium sulfite produces the phenylhydrazine. Now we move to the reactions where we lose the nitrogen, and we have already discussed the reactions where we lose the nitrogen. Remember when you had the diazonium salt, and you added copper metal and some sodium nitrite. This was one of the methods that you used for the preparation of nitrobenzenes. You removed the diazonium part and you added the nitro group in its place. This is very famous type of reactions where you add copper and the salt. Here you added the sodium nitrite. You can add cuprous chloride. This way you will remove the diazonium and you will add the chloro group. You can add cuprous bromide, where you will remove the diazonium and add a bromo group. You can add the cuprous cyanide, where you remove the diazonium and you add a cyano group. All these are reactions that proceed through free radical mechanism. I don't need you to know this mechanism. However, I need you to know that it's a free radical. Whenever you are reacting a diazonium salt with copper metal and you're replacing the diazonium part, the azo part, by whichever is attached to the copper or whichever salt you're using, this is what we call a free radical mechanism. In case of cuprous chloride, specifically cuprous chloride, this is a name reaction and it's called the Sand-Meyer reaction. Sand-Meyer is a scientist who actually discovered this type of mechanism, and it has been employed afterwards in other reagents other than the cuprous chloride, like cuprous bromide, cuprous cyanide. Remember that once you've added the cyano group, you can actually hydrolyze to acids, or you can reduce it to amines. They have another type of mechanism, which is the ionic mechanism. They can react by ionic mechanism, or you can react them with something like potassium iodide. In this case, you will replace the azo part by iodo group. Iodo is the only halogen that will require the ionic mechanism, and you add potassium iodide to the diazonium salt to add the iodo group. You have another reaction, which is you can boil these compounds with water. Remember that these compounds are unstable, and we are always cooling these compounds. We're using ice, and we're actually reacting them at 0 to 5 degrees centigrade. So it's very easy to lose the nitrogen as a nitrogen gas. Accordingly, if you boil them, just boil them with water, you will remove the diazonium and you will add the OH of the water, so you have just prepared phenols. Finally, you can react these compounds with hypophosphorus acid, and in this case you actually end up with benzene. You remove the diazonium part and you end up with benzene. Why would I try to end up with benzene? Why would I remove a functional group like diazonium salt and put nothing in its place? Definitely, you're not going to do this to prepare benzene. Why you're going to do this? Actually, you're trying to prepare something. For example, you have a bromo here and a bromo here. You need to prepare, for example, the dibromo, the meta-dibromo compound. If you look at this compound, both bromo are ortho-para-directing. So how are you going to introduce them to the meta position of each other? This can take place through putting something like an amine here, and then, or an amine here. You can add it at this position or at that position, and you will introduce the halogen parts. One will go to the ortho position of the amine and the other one will go to the para position of the amine. And now you need to get rid of the amine because your final product doesn't contain an amine in it. So what you do is you prepare the diazonium salt of this compound, and then you heat it with hypophosphorus acid and you lose it, and this way you actually have your substituted benzene. So we use this reaction when we need substituents to go into positions on the benzene, which is not logic. related to their electron donating and electron withdrawal capability. Remember that this amine can come from a nitro group. So if you actually need groups that are meta-directing to go into the ortho positions of each other, or groups that are electron withdrawing, they are directing to the meta position to go into the para position of each other, you can actually use the nitro or the amino group according to what you need. How do you need the substituents to orient on the benzene ring? You will employ the nitro group or the amino group, and then you remove them through the diazonium salt and the hypophosphorus acid. Here, the nitro group or the amino group are actually acting like the director of the act. You have a play, you have an act, and you have a director who's actually the maestro of this reaction. It's actually orienting all the substituents to their correct positions, and then it never shows in the act. If you have a play and you're watching a play, you never see the director. He's actually behind the scene. You do not see him, but you know that he's there. If the play is well prepared and you see a good performance, this means that this play had a director in it. You do not see him, but you know that he exists. This is exactly the same role of the amino and the nitro groups in such reactions. You know that they are there because the groups are not oriented in the correct orientation towards each other. So what's going on is that you had another group, you had a director, you had a maestro that was there directing everyone to their position, and then it doesn't show in your final product. You know it was there, but you do not see it in your final product. As we have said, reactions of the diazonium salts are reactions where you either retain the nitrogen, you keep the nitrogen, or you lose the nitrogen. Keeping the nitrogen are two types of reactions. The reduction reaction, where you can reduce them to the hydrazenes using stannous chloride, hydrochloric acid, and sodium sulfide, or you can reduce them to the amines using zinc and HCl. The second type of reaction, keeping the nitrogen, is the coupling with compounds that have a negatively charged or a lone pair of electron atoms. For example, the phenols are one example, and the amines, as I've mentioned, is the other example. You can actually couple them with diazonium salts to give the azo dyes. Both have electrons on them. As I've mentioned, you can put the oxygen here, or you can add the amine in its place and in the final product. You end up with the azo dye, which are compounds that are highly colorful. Finally, we deal with the reactions, the second type of reactions, which involve a loss of the nitrogen atom. And as I've mentioned, these can be free radical mechanism reactions or ionic mechanism. We have the free radical reactions where we actually use a copper metal. You can use copper, cuprous cyanide, or just put copper on potassium cyanide, introducing a cyano group in place of the diazonium part. In all these reactions, you remove a nitrogen molecule and you add a substituent in its place. If you're using a cyano group, then you're adding a cyano group. If you're boiling with water, you're adding an OH. If you're reacting with sodium nitrite in presence of copper, you're adding a nitro group. Potassium iodide, you're adding an iodo group. Cuprous bromide, you're adding a bromo group. Cuprous chloride, you're adding a chloro group. And as I mentioned, this is the Sand-Mayer reaction. It's a very, very famous name reaction. And then finally, we have the hypophosphorus acid. And as I've mentioned, this is a reaction which removes the nitrogens, the two nitrogens, putting nothing in their place. And it's used to orient groups to their correct positions. This way, we have finished the nitrogenous compounds. And next video, we'll deal with sulfonic acids and their derivatives.